So last time we were dealing with single electron tunneling. And we studied some features regarding single electron tunneling, such as Coulomb blockade, and we try to analyze why we observe Coulomb blockade and so on. Today, I'll continue with single electron tunneling transistor. Okay, so the idea is basically it's based on this paper. Now, the idea is simply this. You have a quantum dot, okay, that's connected with the outside world via tunneling junctions. Okay, so these are tunneling junctions. And also you have a gate. Okay, so this is a gate that can be used to control the properties of the quantum dot. So this is actually very similar to a normal construct of a conventional transistor, where in a conventional transistor what you have is again source, drain, and the idea is to control the flow of current from source to drain by adjusting the voltage on the gate. But now the behavior here is going to be dramatically different than what we observe in MOSFETs, simply because, as we have seen in the previous lecture, electrons can tunnel into this quantum dot one by one, or in multiple amounts, but still, each electron that I put in will change the energy of the quantum dot. So the next electron that will try to come in needs to have higher energy. So at some point, this results in blockage of more electrons to fill into the quantum dot. So this is the basis of Coulomb blockade, because of the charges that accumulate in the quantum dot prevents other electrons to get in. So this fundamentally gives us a different operation for the single electron transistor. The way to model this, I mean, I can draw an equivalent circuit to this, and it's not going to look too much different, but you have a leaky capacitor on one end, so we call it C1S. And then this is the dot region. And then you have another leaky capacitor, which is C1D, which goes to here. And then we can ground this side. And then here we have a capacitor, CG. Sorry. And this is VG, and this side is grounded. So we can, also this is the bias voltage that we can apply. This is a schematic circuit diagram that's equivalent to a single electron transistor. It is possible to solve for such a circuit, but after careful consideration, I realized that it quickly becomes extremely complicated to analyze this, because unlike the conventional circuit theory, now you have to deal with single charges, and charges passing through single capacitors, and each of such events will affect the capacitance and so on. So it becomes overly complicated. So I think I'm going to skip that part. But I'm going to directly go to the what you'll get when you measure this. So this is the gate voltage, and this is the voltage that you apply on the quantum dot. Okay, and the intensity gives us, so of course I'm not going to be able to draw it, but the intensity profile will give us the current that flows through the device. And this is sort of what you get. So oops. Okay, and then another diamond shape like this, and then another diamond shape like this. So within these regions, within these diamonds, we can say that the Coulomb blockade is established. So no current flows within these diamonds. Okay? Let me draw the boundaries. Actually, we can define range for the voltages. So this is E over C11, which is defined as the capacitance of this whole quantum dot. And then on the negative side, this is minus E C11. Then this is, this difference actually is given by delta VG, and that corresponds to E over CG. Okay, so also if we solve the equations, we can figure out the slopes of these boundaries. So we can find the region where we got the Coulomb blockade established. So we can theoretically figure out the regions where no current will flow. So I can say no current, again, no current, no current. And beyond these diamonds, the current will start flowing. So as you increase the voltage or decrease the voltage, more and more current will flow through the device. Okay. So in essence, this can be used in information processing, because sort of you have two states. You have the off state, where it's quite stable. So not only you can process information, but you can also store information based on this charging of the quantum dot. So in theory, this can give us a new way of processing the information, but as we'll see, there are some challenges that we need to overcome. So what else? Okay. Do you have any questions? I'd like to discuss some applications. Excuse me. I'd like to discuss some applications of single electron tunneling transistors. One application actually is defining the standard for ampere. So institutions like NIST or PBR or I don't know, places like this use these single electron transistors to define the units for ampere. So how do they do it? They create this quantum dot structure. So let's say we have this semiconducting piece, okay? And then on top of that we have 3 gates. Okay, so let me label them. This is gate 1, this is gate 2, this is the island region, okay, that we can use to modify the, so this is the gate that can control the island potential. And again, as usual, we have source and drain. So the idea for single electron transistor, tunneling transistor, is that we can take electrons into this island region one by one and let them leave the island region one by one. So in a way, we can control the amount of current flow in an extremely precise manner. So the operation is like this. For G1, you have an AC voltage connected, okay, AC bias. So you modulate the bias on the G1, and here you have a DC bias, so we can say G2. Now, in the first instance, they zero the bias on G1. So let me draw the potential landscape. So this is G1, G2 region. This is gate 1 region. What happens is that, let's say these are my electrons. Electrons will reach till this point. So you set the bias between the source and drain in such a way that electrons cannot tunnel or go through this potential that's created by gate 2. And then in the next step, this is what happens. Since we are modulating the bias, this will start increasing. The G1 will start increasing, which will confine the electrons. So these were pretty much free electrons. But now by increasing the bias on G1, you created a quantum dot here, which discretizes the energies, and then electrons need to reconfigure themselves so that they can fill up these discrete energy levels. Then at certain condition, okay, so this is frame 3. So you modulate the island energy in such a way that you end up with a single electron in the quantum dot. Okay? Then in the 4th frame, you keep increasing the bias on G1. So this electron can no longer stay here, but tunnel through this potential. So in the 5th frame, you end up with basically a landscape. So you simply transferred a single electron to the right-hand side of this structure. So you can do this at a very fast rate. Indeed, in the experiments for defining the standards, they transfer, I think, something like 10 to the 8 electrons per second. Okay, so 1 ampere is about 1.609 10 to minus 19 So electrons per second, so the inverse of this guy. So this roughly corresponds to a picoampere of current passing through this device, which is easily measurable. Even attoamperes can be measured, but picoamperes are easily measurable in a lab environment. And the error that they have in system is that plus minus 1 electron in 10 to the 8 electrons. So with that precision, they create a standard for 1 ampere. Okay? That's sort of how they define it. In a very controlled way, they transfer electrons one by one, of course at a very, very fast rate. And with this error, 1 part in 10 to the 8, they can define the unit for current. Of course, yes?
What happens to other electrons in the stage 2?
So what you do is you slightly increase the voltage on the island. Okay? So these higher energy levels will go higher, and then they'll tunnel back. And I'll show how this is possible in a minute. Although you apply a source drain bias, actually electrons can go back since the potential here is large enough still. So I mean, I draw them to look like equal, but still you have a larger potential here. So electrons can tunnel back to where they come from. Okay. So I think the actual challenge is to convert this device into a device that you can carry around so that it will be a reference for instance, I don't know, sensitive equipment. But that's a challenge because measuring picoamperes and also setting up something like this to operate at room temperature is extremely, extremely challenging. Now, another application that, this is the most solid application actually. Also, I don't exactly know how, but I know that this can also be used to define, I guess, or to measure temperature, but I'm not sure how. I remember seeing it somewhere. But there are more interesting proposals. You can, in principle, create single electron tunneling logic, and in this case, if you can really use a single electron tunneling transistor, as I mentioned earlier, you can use it to store charge or carry no current under these stable conditions. So in a way, you can connect multiple single electron transistors to perform arithmetic operations. But room temperature operation means that the island size, the region of the quantum dot, should be less than 1 nanometer so that the electrons can still preserve their coherence. But the problem here is that fabricating such structures is nearly impossible. Even if you can fabricate, its reliability will be, and there will be no reliability because even the tiniest irregularities in the sample will lead to unpredictable results. So one transistor will be vastly different than the other transistors. So the overall operation of the logic circuitry will be unpredictable. So that's the major problem. So still, we need to come up with either new materials that can give us unusually long Fermi wavelengths at room temperature, or single electron transistor logic will be will stay as a niche application that can only be done at very low temperatures. And also there's another problem where typically there's this background charge. So in a way, you cannot completely isolate this island from the environment. There are still charges that are floating around in this system, and that background charge modifies the energy levels within the quantum dot, which again leads to irregularities and unpredictable operation in single electron transistors. So as of now, it looks like we are not going to have single electron tunneling transistors anytime soon in our cell phones or computers, but still they're useful for defining standards and so on. Do you guys have any questions? Okay, so I'm going to wrap up with quantum effect devices. I would like to show you some actual, well, I'm not going to show them, but I'll try to illustrate some devices that has been made to illustrate quantum effects in solid state structures. I'll just give you a few examples, and these examples, these quantum effect devices will be probably the building blocks of future electronics. And they are all related to what we have seen so far, at least the physics that we have seen so far, if not directly related to the phenomena that we discussed. So, as a wrap-up, these devices basically utilize the wave property of electrons. So they will heavily depend on interference of electrons, or reflection, or diffraction, and so on. Also, there will be quantum effects like, again, Coulomb blockade, or again, single electron tunneling, and so on. So these quantum devices depend on the wave properties of the electrons and discreteness of the electrons. One device is electron wave reflection and resonance device. Write it here. So here, what you do is you stack metallic and insulating layers on top of each other. And the idea is to create high-speed electronics. And what they have done, unfortunately, I didn't cite this work, but what they do is they start with a silicon, single crystal silicon, okay, that orients in 1, 1, 1 direction, and then On the back side, they have a metallized region that's called collector. Then on top of this, they deposit alternating layers of calcium fluoride, which is an insulator, and then cobalt silicate, which is a conductor. Okay, so they do this, and they put a bunch of such layers. And then finally, so this is the base electrode. It's gold, okay? And then on top of this, this is again calcium fluoride, cobalt silicate, and then they have again gold here. That's the emitter. Okay. So it's a three-legged device, and the idea is to control the current flow from emitter to collector, or the other way around, using the base voltage. Okay. And then there are some other details, like the whole structure is covered with silicon dioxide, and the layer thicknesses are, so the first layer is like 0.9 nanometers, the second layer is like 2.2 nanometers, this is again 0.9 nanometers, this is 1.9 nanometers, and it goes on like that. So the method to deposit these materials and the choice of materials actually are critical. They use molecular beam epitaxy. So it's a technique that you can deposit layers of materials using epitaxial growth on top of other crystalline materials. And the reason why they choose calcium fluoride and cobalt silicate is that because the lattice mismatch between each of these layers can be carefully optimized. Now, the idea in this device is, now let me shade the regions, insulating regions. These regions are insulating, okay? So the electron's motion, so if you try to send an electron from collector to emitter, you need to tune the voltage, the potential, across each barrier carefully, that the electron can tunnel through these barriers in a constructive way. Let me explain what I mean. So I'm trying to explain a resonant tunneling mode. What happens is, take a black pen. So this is the emitter side. Okay, this is the first calcium fluoride layer. That's an insulator. Okay, and then that's the second calcium fluoride, and that's the third calcium fluoride. Then these are the conductive regions, and the way we connected them is, so these two, so if you think about it, let's see, this is the collector side, so this is silicon. Then I have my first, so it should be connected to here, sorry. Okay, so this is base to, sorry, this is base to emitter, excuse me. So This is VBE. So in this case, this is my emitter side. So it's this junction. And this is the base side, which is this junction. So it's like I'm going from top to down, top to down. Okay, the arrows indicating the same direction. So the voltage between the base and emitter, there's only a single calcium fluoride layer. Okay, and then this one is VCE. Okay, collector to emitter. And an electron that starts its journey from the emitter side will do resonant tunneling through these calcium fluoride layers to reach here. Let me draw what I mean in this IV curve. So this is the current that you get from the collector, and this is the voltage between, it's in volts, collector and emitter. The range is, it starts from 4, ends at 8, so we have 5, 6, and 7 in between. And what you get is something like this. I'm gonna need this one. So in one case it just increases, and then somewhere around here it decreases. It does something like this. This is for VBE equals to 3.3 volts. So when you apply, let's say this is grounded, and you apply 3.3 volts to here, and then you tune the voltage between the collector and emitter, so you keep increasing the voltage. What happens is that the current gradually increases, and at some point it goes to where you started. And then it increases and it goes down again, and then it keeps increasing. What's happening is that electrons in this regime sort of doing a resonant tunneling. The interference between the tunneling of electrons through these layers are enhanced by the increasing voltage till a point where you now have, you don't no longer satisfy that resonant tunneling condition. So the resistance increases, although you increase the voltage even further. So we're talking about a negative differential resistance. Although you increase the resistance of voltage of the device, the current that you get decreases. So let's take a look at another base emitter voltage. One of them does something like this. So it increases, and then it goes down, and then goes up. So this is VBE to be 2.6 volts. And then finally, there's this one. It goes up and then goes down. And does something like this. So this is 1.9 volts. So for each base and emitter voltage, you get a different collector emitter characteristics, because now you control basically the resonant tunneling condition between these three wells. So that's one quantum device that you can fabricate and show its operation, but I'm not sure exactly what purpose this device will serve. So, yes, please.
Can you explain why this dropped suddenly?
Let's do it this way. Now let me show you. Let me solve some equations, and perhaps it will become more clear why we can see such a drop. Because it's not immediately obvious why we see that drop. Because we need to see basically how we tune the resonant tunneling condition, which comes from the fact that you start with an electron here, and you have certain tunneling probability here, and certain tunneling probability here and here. So once you send an electron to this conductor, this electron that is being transferred here should still have a high transmission tunneling probability through here, but that's not always the case. If you modify the energy of electron that's within this region, then you can destroy that tunneling condition in a way. So let me solve the equations, and perhaps it will become more clear. Any other questions? So, now let's imagine a simple case where we have two potential wells, okay, that are connected to each other. And what I'd like to solve for is perhaps this. What happens if I start with some wave function, some electron in this well? Let me label this as well A, and this one as well B. What happens to the electron that I have in this well after certain time t? So the overall wave function of the system can be written as such. I'm going to have some time-dependent amplitude times the wave function in A plus some bt in wave function in B. So the idea is this. If this separation is sufficiently close, and if this barrier, we can modulate that one as well. If I let this system relax and let it go, at certain time, I'll have some probability of finding the electron in well B, okay? Because the tail of this wave function will leak into here, okay? And then if I try to solve the equation, I'll see that because of this tunneling, there's a probability of finding the particle in well B. So I'll quickly write down the equations that will govern this whole process. So we can write down the time evolution as such. I'll do this in one dimension. So plus VA, which is the, so I'll say VB. Also, I'll define this as V0, the barrier height, so that I'll have flexibility to tune it up and down. I'm going to VB minus V0. So to simplify things, I'll confine myself to the case where I have VA and VB to equal to each other. So of course they apply to the wave function phi of t. So if I plug in this expression to this Hamiltonian, to the Schrödinger equation, what I'll get is dA dt equals to minus I omega A at minus I kappa AB of bt, and then dBt over dt equals to minus I omega B bt minus I kappa BA at. So I end up with a coupled equation that gives the amplitudes for states in A and B. So it gives two equations that are coupled to each other. When I simultaneously solve them, I can figure out what A and B is. So I can figure out the time evolution of these states. Now, let me get rid of this one. There are some constants that I've written over there. WA is, omega A is EA over H bar. Omega B is EB over H bar. And then kappa AB equals to kappa BA, which is, let's define it as kappa H bar K over LM. L is the length of the well, or both wells, times e to the minus KL. And here K is written as 2 pi H bar divided by square root of 2m V0 minus E. Okay. So if I solve for these equations, that's what I'm going to get. So let's assume at A0 we have, so t equals to 0, we have our electron to start in well A. So if I solve for these coupled equations, that's what I'm gonna get. The amplitude squared is going to be cosine squared kappa t, and b of t squared will be sine squared kappa t. Now, the condition for time can be written as such, where n starts from 0, 1, 2, 3, and goes. And this condition gives us time when the electron transferred into either of the wells. Which means that in that time intervals, electron is either in well A or in well B. There's no probability of finding the electron in A or B, or, you got the idea. So for n pi over kappa intervals, it will be back in A. So this, in a way, defines as a condition where electron oscillates back and forth between these two wells. So if we come back to your question, what we are trying to do is we adjust these parameters in such a way that we maximize the tunneling probability Okay, so now of course we are not dealing with two well system, but we have multiple wells, and also electron can leak out of the system. So changing basically this collector emitter voltage beyond certain value or lower than certain value will destroy that tunneling, resonant tunneling condition. Okay. So, oops, I was going to make a quiz, but next time. Okay, I spoke too much. Okay, so what's that? Yes. So I'll talk about a few more devices next week, and then I'll start discussion of superconductivity and superconducting mesoscopic devices. Then, yeah. Thank you. Any questions? Olur. Tamam.